Uh, Welcome to this lecture number 13 of the course Computational Hydraulics. We are in module 2 numerical methods, and in this particular lecture I will be covering unit 9 finite volume method overview. Learning objective for this particular unit. At the end of this unit, students will be able to discretize the derivatives of single valued one dimensional functions using finite volume method. And they will be able to derive the algebraic form using discretized ordinary differential equation and boundary conditions. Let us consider our general equation in terms of phi, where phi is a general variable in terms of x, y, z and t. The first term is temporal term, second term is advection related term, and first term in the right hand side, this is related to diffusion, f is related to other forces, and s phi is related to sourcing term. And this lambda phi and epsilon phi, these are problem dependent parameters, and gamma phi is the tensor or coefficient tensor for the right hand side. Now, this is a general equation. We can write this general equation as R, where x represents, this bold x represents x, y, z directions. In the method of weighted residual, the residual R can be written as this one. This is our left hand side of the equation. With minus sign, we can include the right hand side. Now, with this, if we write this weighted integral of residual and we equate this to 0 for all W L corresponding to a particular L, we can write this, where this omega represents the domain. Now, with this, if we approximate this W L or weight function as Dirac delta, that means at x is equal to L, x is equal to L, this is 1, Dirac delta equals to 1, otherwise this is 0. So, with this weight function in collocation method, if we apply this Dirac delta instead of W L, we can write this one as R x L t 0. That means, this integral can be approximated as R residual x L t. That means, if we evaluate the residual at point L, then and we equate it to 0, then we can get the approximation in terms of method of weighted residual. Interestingly, in our finite difference method, we have used similar concept for a particular location L. We have used Taylor series expansion to approximate the derivatives with the help of neighboring points. So, this is similar to our finite difference method. Now, with this, if we apply this WL such that for a particular subdomain omega L, omega is the domain and omega L is the subdomain. For that subdomain, we have weight function 1, outside that subdomain our weight function is 0. So, with this information, if we proceed and write our method of weighted residual, so we can write it as this, where WL for small domain or subdomain, we have this equal to 0, and this is similar to finite volume method. In finite volume method, our approach is to reduce the elemental error for a particular problem with given differential equation. R is in terms of given differential equation, and this limit is for subdomain. So, with this we can start our finite volume method. Now, we need to define this Gauss divergence theorem. As per Gauss divergence theorem, suppose this omega is the volume bounded by a closed surface S, closed surface S, and a vector field defined, and a vector field defined in this omega and on S. If S is piecewise smooth with outward normal, this is unit normal, and a vector is continuously differentiable, then with triple integral, which is actually volume integral over whole subdomain, this is our domain for individual subdomain. If we apply this, we can write this one in terms of surface integral, where this del dot A will be transferred to A dot n ds. So, in this case we are transforming the volume integral to surface integral, volume integral to surface integral, and n is outward normal, A is any arbitrary vector, and this is our del operator. Now, let us utilize this concept for finite volume formulations. In divergence theorem, we have talked about the surface. If we consider a particular small elemental volume where this is our delta x size, this size is delta y, and vertical side is delta z, then we can write individual components for this particular domain and surface. In this case, basic assumption is that area is having direction, and direction of area is always outward positive. So, outward in z direction with green arrow, these are positive, red arrow in y direction and orange arrow in x direction, these values are positive. If we utilize this, so area in z direction, this is a z plus del z by 2 into k hat, this one is positive in positive z direction. This is negative because it is pointing towards negative z direction. Again, this is pointing towards positive y direction, this is pointing towards negative y direction, this is pointing towards positive x direction, this one is pointing towards negative x direction. Now, individual values of x plus delta x by 2, this is equal to x a x minus delta x by 2, this is actually del y del z. Now, whatever problem we have solved in our finite difference approach, we can also solve those problems in finite volume methods. So, let us consider first our ordinary differential equation and boundary value problem with two boundary conditions. One side, this is specified boundary, this side is impermeable boundary condition. We have one leaky confining layer, one unconfined aquifer, bottom we have confined aquifer, and at the base we have impervious bottom. This is a groundwater table position. So, with this we can mathematically conceptualize the problem in terms of this differential equation. In our finite difference approach, we have utilized this differential equation, but the basic differential form for a particular confined aquifer system, this will be T del H by del x d by dx. Now, in this case other things are known, that is left hand side we have Dirichlet, right hand side we have 0 Neumann, and HWT is represented in terms of C0, C1, C2 in nonlinear form. In case of finite difference, we have discretized our domain in terms of some node points, and we have represented these nodes as x naught, x1, xi minus 1, xi, xi plus 1, xn minus 1, xn. Thus, in this case we have n number of segments available, n number of segments starting from 1 to n. But in finite difference approach, we divide this length 0 to L into a number of elements. So, first case, this is our xi. Xi is defined at the center of the element. So, this is actually del x, again x n minus 1, this is with del x length, and individually for xi, xi minus 1, x plus I plus 1, we have used the same discretization with elements. Now, these individual lines, these are actually element boundaries. For each element, we will have element boundary. For n point, we have this del x by 2 length extra. So, for this del x by 2, we need to define separate elements. So, for 1 to n minus 1, we have n minus 1 number of elements, and for xl and xr, we have 2 extra elements. So, all total we will have n plus 1 number of elements in this case. However, we can utilize a different concept where we can divide this 0 to L domain into different elements of different sizes, starting the cell center for the first element as x 1. Now, for discretization, let us use this concept, first one, because this is equivalent to our finite difference domain discretization. Let us discretize our governing equation. Centered node or cell center for the middle element is P, and cell center for left element, that is W, and each side we have E. So, for this one, if we integrate this equation, our main governing equation, with this limits omega p, this omega p represents this central element, and we can equate this to 0. So, if we utilize this, then we can write this into two parts. First part is with derivatives, and right part is equivalent to sourcing term. Now, with this, if we discretize the left hand derivative part, this using this Gauss divergence theorem, this is equivalent to area integral, and area integral with t dh by dx I, this is our vector, this vector dot n into ds. N is the outward normal for this element from our divergence to or volume integral to surface integral, in this case for n ds and I dot n hat, we can write it with a component in x direction, area component in x direction. So, this integral can be written as summation, where T dh by dx, this is evaluated at element boundary, this is at P, this is element boundary on east side, this is at west side. So, Ax E and Ax W, these are area values corresponding to this Ax W and Ax E. So, with this in uniform grid system, this is equal to T E, T evaluated at E, and this is H E minus H P, this is forward derivative, this is again evaluated at W. At W we can write it as H P minus H W divided by del x. With these derivatives and right hand side sourcing term, that is actually omega p h d omega, this is equivalent to H p into del x 1 into 1, which is the volume of this element. So, we can write this as H p into del x, and the right hand side second term H w t, we can use this C 0 C 1 C x square C 2 x square dx. In this case x w to x e, this is a limit. So, with this we can integrate it, and in compact form this can be written as T e H e minus H p by del x, T w H p minus H w by del x, and this C conf is multiplied with this one. So, with this, if we proceed with the approximation that T equals to T w t and x c minus x w, which is del x, we can write this that H e minus 2 H p plus H w by del x square, this is C con by T H p, because in this case putting the integration limits, we can approximate the right hand term. In this case, if we compare our equation with the finite difference one, so this is for ith one, this is P, E is equivalent to our I plus 1 and W is equivalent to I minus 1. So, left hand side is similar. So, let us look into the right hand side. Right hand side, one extra term is coming, this is extra. If we approximate this, because x c is nothing but this x p plus del x by 2 and x w is nothing but x p minus del x by 2. With this, if we approximate, then we will get 1 by 12 del x square. Now, for left boundary the situation is same, but slightly different. In this case this length is del x by 2. So, x l is situated at del x by 4 distance. So, distance between for this E phase we have distance between E and P, this is actually del x by 3 del x by 4, and left hand side we are taking derivative using P and H naught. H naught is the specified value at this point. So, with this if we approximate the thing for left hand boundary, we can get similar discretization, but H naught is known, H p and H e are unknown. So, we need to transfer this H naught on the right hand side. So, final equation will get like this in terms of H e and H p on the left hand side, and these values are known on the right hand side. So, in simplified form this is the thing, but in this case 1 by 48 del x square is the extra term. Now, if we utilize the same concept for the right boundary, so we will have only x e term E phase, and E phase we are getting this one will be 0 for east phase, and W term will be there. So, we can write this in terms of H p and H w. So, in this case we can again approximate this, and for east right boundary we can again get the simplified equation in terms of H w and H p. So, for with the interior equation left boundary and right boundary we can solve the actual problem. This is similar to finite difference technique, but we need to determine the values at the end points x naught and x n. We can use our Neumann boundary condition, and we can involve this x r point, x n and x n minus 1, and we can relate this x n x r x n h n minus 1 like this. So, in this case we can get the h n value from this equation. So, we have got all the values x at point x naught, this is defined at point x n we can get from this equation. For interior points starting from x l to x r, we can use the boundary condition and interior governing equations. So, now with this we can solve the problem. Thank you.